Hello and welcome to the class notes for 7.2. This is going to cover ionic bonds and ionic compounds. And we're going to look at what we talk about with compound formation and ions. So let's start with the idea of what an ionic bond is. An ionic bond is actually the attractive force between the cations and anions. Cations have a positive charge and anions have a negative charge. So that attraction between those oppositely charged particles is what makes an ionic bond. That's a little bit of a different explanation than you had in your book explanation, which talked about electrostatic forces of attraction. And that is a little bit more complex way of saying that you've got attractive forces between cations and anions, and that's what makes up ionic compounds, and that is going to be the attractive force behind an ionic bond. So let's talk about how those compounds might be formed. In a situation where we would have a metal coming into close contact with a non-metal, what's going to happen is the metal would give up electrons and transfer those electrons to the non-metal to make both atoms into stable ions, okay? And then it is their opposite charges that attract them to form an ionic bond. So I have an example here that I'm going to show where I'm showing the dot structure for sodium, because sodium is in group 1. It has 1 valence electron. So that's what I'm showing here. For chlorine, which is in group 17 and has 7 valence electrons, that is going to be this metal reacting with this non-metal. And in this dot structure type of model, what we're going to say is that in a very powerful, very exothermic reaction, we're going to have a transfer of sodium's 1 electron to chlorine, so that sodium now has a full set of valence electrons that is the same electron configuration as the noble gas that comes right before sodium. So that would be neon. And then on chlorine's part, it will gain a valence electron and have an octet that's the same as the noble gas that follows chlorine, which is going to be argon, okay? So if these are combining and reacting, what we end up with is sodium, which, since it's now lost an electron, will have a 1+ charge. And then the chlorine, which has gained an electron, will then have a 1- charge. Both would be stable, and actually this would be then a situation where this cation, this positively charged ion, is going to be attracted to this anion, the negatively charged ion, and there would be bonds formed between those cations and anions. So that's the attractive force. Another situation that might occur with compound formation is that you already have a metal cation and it's going to be attracted to a non-metal anion. So those positive and negative charges would have already existed. So it doesn't always happen that this is how, for example, sodium chloride is formed. It may be that the sodium ions are already in this stable form, and the chloride ions are already in this stable form, and they combine in this ionic compound. Okay, so that gets us to the idea of what are we referring to when we talk about a unit. So for a chemical compound, we can have the simplest unit and refer to that in different ways. You're used to using the term molecule, and a molecule does not work for ionic compounds. Molecules are referring to compounds that have shared electron bonds, as opposed to ionic bonds. For ionic bonds, we use the term formula unit, and the abbreviation for that is FU, okay? The definition of a formula unit is that this lowest whole number ratio of ions in an ionic compound, and I'll give an example of this. The lowest whole number ratio of ions in an ionic compound, and we'll just use that same example that we had up here, would be, for example, if we show the compound formula for sodium chloride, which is 1 sodium ion and 1 chloride ion. When we refer to sodium chloride and a formula unit of sodium chloride, we're really referring to the lowest whole number ratio, which for sodium and chlorine is a 1-to-1 ratio. However, if we have a solid that's formed and is sodium chloride, it actually is sodium ions surrounded by many chloride ions, which are each surrounded by many sodium ions. And what we really have is just an explanation of the ratio that exists between these. Okay, so if we have, for example, these 4 chlorines, then we would need to indicate that we also have 4 sodiums. Okay, so it is really just a ratio, and we would never have just 1 sodium with 1 chlorine in a discrete unit. So that's what I mean by existence here. The existence of this is that the formula unit, which is our lowest whole number ratio, just shows a ratio of ions in a crystal, but the formula units do not exist as individual units. And that's different from the concept of molecules, which do exist as individual units. Okay, next let's go through the class notes with respect to properties of ionic compounds. So the properties of ionic compounds are very specific, and we're going to use them in comparison to something we'll learn a little bit more about later, which is covalent compounds. For properties of ionic compounds, your keys gave you those properties in that most ionic compounds are solids at room temperature. Also, ionic compounds generally have high melting points. These two actually kind of go hand in hand in that it's the high melting points that means that if they're at the temperature that the room is at, which is usually about 25 degrees C or around 70 degrees Fahrenheit, 68 to 70 degrees Fahrenheit, that is not a high enough temperature to melt these ionic compounds. So they're going to be in solid form at room temperature. So let's talk about why that is. Ionic compounds, we know, are composed of cations and anions that are bonded to each other, right? These are through ionic bonds. These strong attractive forces, which are the ionic bonds, result in a very stable solid that takes relatively high temperatures to melt. And that's compared to ionic compounds that have a similar size for a formula unit versus a molecule. These ionic bonds are what must be broken to melt the ionic compound, and ionic bonds are very strong. That means that ionic bonds would require quite a bit of energy or relatively high temperatures in order to melt. So for example, something like sodium chloride would melt in the somewhere maybe 700 plus degrees Fahrenheit in order to get it to its melted form, into its liquid form. Okay, strong bonds, and that means high temperatures or relatively high melting points to get them out of their solid form. The third key that we had, which is a property of ionic compounds, is that ionic compounds can conduct an electric current, and I added the word only in here, and you might want to add that to your key, only when melted or dissolved in water. What that tells us is that ionic compounds in their solid form will not conduct electricity. However, if we dissolve those ionic compounds in water, they will conduct electricity, or if we melt them. Okay, so that leads us to wonder, what is it when something does conduct? What is conductivity? And that's what I have here. Okay, conductivity occurs if we have charged particles. Those might be electrons, as in the case of metal solids conducting, or it might be ions, which are also charged particles, cations and anions. They have to be present, and they have to be able to move freely. So if conductivity occurs if charged particles are present and able to move freely, let's consider ionic solids and the fact that ionic solids do not conduct electricity. So let's think about what ionic solids are. If we have an ionic compound, for example, we'll use sodium chloride again, where the sodium and the chlorine are locked in this repeating array. And this would go on and on and on and on, okay? So what is our criteria for conductivity? We said conductivity occurs if we have charged particles. Well, here we do have charged particles, but we have to have those charged particles able to move freely. And in an ionic solid, the charged particles exist, but they cannot move. They're locked in this crystalline structure because of these ionic bonds, okay? So what's different when those ionic compounds are dissolved in water or melted? Well, what happens is we find that they do conduct electricity, and we want to think about why. When we dissolve ionic compounds in water, what happens is that our ions are released from the crystal and able to move freely. They're going to be surrounded by water particles, and those water particles are going to have the opposite charge, partial charge for the water that is toward the charge that is opposite them, okay? So I'm gonna kind of set this up. We'll talk about this quite a bit more when we talk about polarity later. But what's going to happen is that the positive end of the water molecules will point toward the negative side, or the negative ions, where the negative side of the water molecules will point toward the positive ions, the cations, okay? So each of these will have some situation where they're surrounded by water. But the point here is that these ions are no longer locked in this crystalline structure, and they can freely move throughout the solution. So that's what's happening when we have ionic compounds dissolved. For example, in water here. Okay. Something similar occurs when we melt ionic compounds, in that instead of being locked in a crystal like this, all of a sudden our particles are free to move, right? They can move past and around each other. Remember, we talked about how liquids have flow as opposed to being locked in a crystal like solids. So because these particles are able to move and go past one another, we can have conductivity of electricity. Okay, so that's the difference between ionic solids, which do not conduct. Their charged particles are not free to move. And ionic compounds, which are dissolved in water, are melted. They have charged particles that are now free to move. And that's why we have conductivity of electricity for ionic compounds, which are melted or dissolved in water.